Welcome to today's Research Pays Off, and I'm going to hand it over to our speakers, Raul and Ceren.
Thank you, Lauren. Good morning, everyone. Thank you for attending this Research Pays Off. I'm going to be talking about improving field moisture monitoring of recycled bases with Ceren. So let me first introduce the co-investigators and co-authors of this study. Ceren Aydin, who is a PhD candidate from Michigan State University and was an intern in MnDOT for about 8 months. Dr. Bernard Isawokai, my supervisor. Oh, I think I nailed this time his last name. It's been years on me working on it. And Professor Bora Chetin from Michigan State. Before we go into all the technical details, I first want to acknowledge and provide a special thanks to MnROAD staff and the Office of Materials and Road Research, MnDOT leadership, for working with us on this collaboration and this study. This list is in alphabetic order. I want to name the people that really help us throughout the study. Jeff Bronner, leadership, for helping us navigate all the approvals and help us with the setting up the internship, the NSF internship, and all the support. Emil, Troy, Craig, Steve, Dan, and Jesse, Bob, and Jeffrey at MnROAD for all the help that we have during fieldwork. Without their technical support and the extra efforts that they provided in the field, we'll have not accomplished this study. And Joe Vols for his help setting up our work here in the lab at the Office of Materials and Road Research. So thank you, all of you, for your contributions on this study. I want to just mention this for the research institutions and universities that are right now tuning in. This is a very useful program that NSF provides. So if you have an NSF project or are planning to get involved with NSF, I highly recommend you to reach out to Professor Chetin so you get some ideas about what this internship is all about. For us, has been very productive, not just technically, but also we have a lot of positive outcomes coming from this internship. For the project managers that are out there, I just want to highlight some of the benefits that we as MnDOT as organization got out of this internship. We have about, in terms of, to put some benefits, we have an engineer working full-time for us for about 8 months, which was Ceren. We have donation of instrumentation. We have these Sherpa-Ray sensors that were installed in the last cycle of reconstruction. There were 10K each. We have 2 weeks of a group of 3 grad students coming to help us out during the reconstruction of MnROAD for all the geotech work. That was cost about $13,000. So in total for 8 months, we benefit from about $73,000. So that was very beneficial in terms of work done and the support that this collaboration with NSU was provided. So here's some pictures of the authors of this study here during TRB representing this work. And then on the right, we have here the MSU team helping us out during the installation of this week in geotextile, one of these projects that we have at the last cycle of reconstruction of MnROAD. So before I hand it over to Ceren, I want to explain why we did this study. I want to give you the research motivation. First, I'm going to put my practical hat on, and really this study started as a means to provide support to the MnROAD folks. Ben and his team, they have a big program, reconstruction program, and included an installation and monitor of sensors. So the idea was to provide support on the geotechnical aspect and help them with the installation and calibration of the moisture sensors. So that's how this thing started. Is okay. We need to help these guys. Let's figure out a cool project that we can provide the help, but also get some cool research activities going on. So that's kind of that. First, the motivation was more practical, but then as we were working on it, evolved into something that can be applied for other DOTs and have more that has more implications. So we know that moisture dependency is extremely important for pavement foundations. We know that residual modulus and stiffness of your foundation heavily depends on your moisture content. And moisture fluctuations heavily affect pavement performance. And we have here in northern states, we have the actions of freeze thaw, seasonal variation of moisture, flooding due to heavy rainfalls. So we understand how important is monitoring moisture in our foundation. We also now have a big pressure of using recycled aggregate bases, which are non-classical materials for monitoring moisture. These sensors that we're going to be talking about were not developed for this type of materials. So we want to understand how these sensors work with these non-classical recycled materials that include recycled asphalt pavement and recycled concrete aggregate. And we're going to go a little bit into the nuances of why these are a little bit complicated when we're talking about monitoring moisture with the principles that we're currently using. And last but not least is this big pressure on developing geotechnical asset management for DOTs. DOTs are trying working on developing their programs and monitoring the performance of their assets, which include, for some of them, some DOTs, their pavement foundations. So this is also very beneficial for them. Now I'm going to put my academic hat. I'm going to get a little nerdy. The other aspect we wanted to explore with Ceren and Bernard and Bora was getting into the fundamentals of the dielectric of geomaterials. As Ceren is going to be explaining, we use dielectric to measure volumetric water content to estimate the moisture content of your geomaterials. So we want to understand, okay, what are the parameters that influence the relationship between the volumetric water content, and dielectric? Is the relationship linear? Is it nonlinear? Why is it nonlinear if it's nonlinear? What are the effects of each component? So what is the effect of having a little bitumen on your aggregate? What is the effect of having unhydrated cement on your aggregate on the dielectric? Furthermore, is the structure of your fabric, of the structure of your soil, the internal structure, important on the dielectric or not? So here I'm showing an example of two soils that have the same density. However, we all know that have different stiffnesses due to the fabric, due to the internal structure, and different shear strength. What about with the dielectric? This internal structure have an impact on my global behavior of the dielectric? Ceren is going to show you some preliminary results in understanding these questions. And also, when we do fundamental work, we expand, we open the door to cross collaboration among teams. So what we are trying to get is to understand the dielectric as function of their constituents, so we can, work in other topics, like, for example, help concrete teams that are working on understanding the curing process of that material using dielectric principles as well. Or, for example, assisting Dr. Segeye with his road doctor program using GPR-based measurements for estimating moisture, or helping also Dr. Hall with his DPS program that is based on dielectric-based measurements of asphalt. So this fundamental work can help, bridge collaboration, can start new collaborations. So that was the other reason for starting this. And with that, I'm gonna let Ceren take the floor.
Thank you so much, Raul, and hello everyone, welcome and thanks for joining us today. So I'll be taking over the research with the research objectives. First and foremost, we wanted to understand how these sensors, these moisture sensors, volumetric water content and the metric section are working. We basically wanted to have a deeper fundamental understanding for the sensor output and for the data that we are actually targeting with. In our case, it was the moisture, volumetric water content, and also the metric section. So following that, we wanted to develop calibration equations for the granular materials, for the materials that we are planning to use during the MnDOT reconstruction. And we also wanted to evaluate the performance of this sensor, both of them, for the recycled materials, considering the popularity of this recycled material use because of their sustainability aspect and also their cost effectiveness. this. So as a result, one of the biggest objective after performing all this work to understand how these sensors are working was actually developing an installation guidelines to make everything smoother and easier in the field, so we can have non-problematic installation, so we can target actually high survival rates. In the first step, of course, it is the initial survival rates for both of these sensors. So let's get to know our sensors, because in today's presentation we're going to talk about them whole a lot. So we have two moisture sensors. The first one is volumetric water content, TEROS 10, and the other one is metric suction, which is TEROS 21. As you can understand from their names, one is measuring the volumetric water content and the other one is metric suction. As you can see from the figures here, geometrically, they are also different. They have different sizes and they have different actually shapes. In addition to the geometrical differences, one of them, which is volumetric water content, is a little trickier to work with because you need to have calibration equations that are helping you to transform the sensor output, which is in millivolts, to the target value that you wanted to get, which is in our case volumetric water content. However, for metric suction, you don't need any kind of calibration procedure. The sensor is going to give you the metric suction directly. Apart from the differences, there is one big common aspect for these sensors, which is the feature, the property that they are using to give us these data. So it is for this moisture sensors, we are getting help from the dielectric permittivity properties of materials. In our case, this is going to be soil. And for those who are not familiar with the dielectric permittivity, it is in a simplest form. It is basically the ability of a substance, in our case, this is soil medium, to hold an electrical charge. However, volumetric water content will give you directly the dielectric permittivity, while metric suction is actually using the electric permittivity indirectly, but it is eventually, at the background when this metric suction sensor is working, it is still getting help from that properties of the soil mediums. And here is actually a nice comparison picture that Raul took. So on the left-hand side, you are seeing a very old, ancient moisture sensor, probably from very early stages of the MnDOT facility. And on the right-hand side, you are seeing the one that we actually installed last summer. And as you can understand from the scale, it was obviously much harder to install the big one. I really respect for all the technicians and engineers for installing these sensors. It seems like a huge effort, and it is apparent that our job this time is easier. However, to make sure the reliability of the data that we are collecting during the throughout the service life, we wanted to understand some key parameters to increase the efficiency of this moisture sensors. All right, so I'm now going to continue with the laboratory efforts. So for both of the sensors, we are going to have a little bit of laboratory efforts and also some field findings to understand actually if our developed installation guidelines worked and what are the results that we are getting so far. But majority of this presentation will be the laboratory efforts. So first of all, to understand the volumetric water content, we need to have more ideas about the dielectric permittivity. We already said that it's an ability for a substance, for soil, to hold the electrical charge. Now we are going to take a look at something called dielectric constant, which is nothing but the ratio of the permittivity of our soil to a free space, which is in our case, it is going to be air, which is dielectric permittivity is equal to 1. And understanding this scale on the right top of the slide is also important because I'm going to touch bases on that when I share the laboratory findings with you. So this scale is actually really useful because it shows different materials have different dielectric constant. For example, we just said that air has a dielectric constant of 1 and water has a dielectric constant 80. So you can see that actually air and water are here representing the two extremes of the dielectric constants. And we also see that soil minerals somewhere around 2 to 5 dielectric constant. Let's keep this in mind, but let's look at the materials that we use in our study. So Here we have a wide selection of the recycled materials. We have coarse RCA, we have fine RCA, we have a combination of RCA with the wrap, and we also have natural aggregate, virgin aggregate limestone. And in addition to this granular materials, we also wanted to have clay, and clay is actually used for the second moisture sensor more, which is the metric section sensor. So before jumping into the installation technique, let me share something with you. So this all moisture sensors that we are using, both of them, volumetric water content and metric suction sensor, they are actually originally developed for the agricultural applications where the soil gradation is finer compared to base and sub-base layers, and also the characteristics of the material that they are having in the agricultural field is much more different than you have for the granular mediums, which is the biggest difference is the cohesive characteristics. So if you go ahead and follow the instructions for the installation coming from the manufacturer manual, it's basically you have a borehole in the field, and then you just have your needle structured sensor, and you're basically pushing that sensor needles into the borehole wall. So it seems very doable and it seems easy to do in the fine-grained medium. However, if we are dealing with compacted, high stiffness granular materials, you can understand that it's not going to end very well for us. Either we are going to just damage the sensor, or maybe we're not even going to be able to install the sensor because of this stiff granular structure. So in order to eliminate this possibilities, we said that why don't we have pilot holes that can make our job easier. So we took the easy route actually, and we found the simplest tool in the laboratory, which is a simple screwdriver. The only part that is important here was to have a screwdriver with a similar geometry to the sensor's needle. So it was actually pretty satisfactory what we have in the lab. So basically we created this pilot holes, and then the rest was just installing the sensor into the pilot holes, and it worked really well for us in the laboratory. And here are some results that we obtained from our laboratory efforts. So first of all, right now you're looking at the 6 different graphs. Overall, we have seen the same trend for all the granular materials that we tested. So I wanted to actually take your attention to the first one here for the coarse RCA to make things a little easier for us to understand. So first of all, when we were doing testings, we wanted to see if the compaction degree is actually a factor affecting this relationship between the dielectric permittivity and the volumetric water content, because we know that when it comes to achieving a uniform foundation layer, there might be some challenges in the field. So we wanted to see if we really need different calibration equations for the loose state and for the compacted state. So here the red squares are representing the laboratory loose and the black squares are representing the laboratory compacted. And if you take a look at the first graph, you will see that there are in some volumetric moisture contents, they are slightly different, but overall we didn't see its effect. So we can even say that they yielded very similar results. And the other thing that we wanted to check here is actually the comparison of the experimental findings in our laboratory with the Top et al. 1980 calibration equation, or the equation that is actually commonly used to determine the volumetric water content from dielectric permittivity, and also the manufacturer's equation. So when you purchase these sensors, they are coming with the manual, and in the manual you actually have already calibration equation for you to get the volumetric water content. However, let's remember that this actually calibration equations coming from the manufacturer, it was also developed for the agricultural applications. So where you have mainly clay-dominated soils, where you have a finer gradation and cohesive. So it was really important for us to see how our findings are different or similar for the granular materials. And if we take a look at the again first graph, we actually saw a big difference, especially for the higher volumetric water contents. And let me try to explain what actually I mean here. Let me just choose a pen here. So let's take a look at the dielectric permittivity 15. So if you have the electric permittivity 15 measured with your volumetric water content sensor, the experimental results are telling us that for coarse RCA, you're actually having a volumetric water content somewhere around 15%. And now let's take a look at what would happen if we go ahead and use the manufacturer or commonly used Top et al. Equation. So in that case, it seems like we actually have somewhere around 25%. So 15% to 25%. And if you are dealing actually with the granular materials, we all know that this difference is a huge difference. This difference is going to definitely have some effect on the stiffness characteristics. So basically, you are talking two different state of materials for 15% volumetric water content and 25% volumetric water content. So it was actually good for us to see that, okay, for the granular mediums, we need our own soil generic calibration curves. So in order to make the things easier to understand, so let's ignore my ugly drawing here. So let's take a look at the relationship that we observe for this granular material. So here is we're looking at the dielectric permittivity and the volumetric water content, and results showed us there's actually a bilinear trend between these two properties. So it is almost so there are two distinct parts where the rate of the dielectric permittivity change is different. So if we take a look at the first part and the second part, as you can see here for the second part, with a little bit of increase in the volumetric water content, you are going to see a jump in the dielectric permittivity. So we wanted to understand what exactly causing this two distinct behavior, and we decided so far that there are actually these two parts are actually being controlled different mechanism. The behavior is controlled with different mechanism. So we decided that here in the first part, the air presence is actually dominating the dielectric behavior, because if you remember in our dielectric constant scale, air was corresponding to the minimum dielectric constant, which was 1. And in the second part, it seems like water actually dominating the system as a continuous phase, and we actually see a high jump in the dielectric permittivity corresponding to high volumetric water contents, because it has a huge dielectric constant. And if we take a look at this transition point, we are still working on understanding what is the control mechanism for one behavior to another behavior. So we are still actually working on it. So after running these experiments in the laboratory and obtaining the calibration equations to be used in the granular mediums, for the granular mediums, we wanted to take our dielectric understanding of the dielectric permittivity to further. So we realized that there are actually composite modeling equations in the literature that are available. So these equations, right now you're looking at two of them, one from 1968, the other one is from 1988. Overall, even though this seems a little complicated, overall what these equations are doing, it is they're giving you the overall system's dielectric permittivity, which is called effective dielectric permittivity. And how? Basically, on the left-hand side, you have your target dielectric permittivity, soil's dielectric permittivity, and on the right-hand side, you have individual components dielectric permittivity with some equation parameter, which I will be explaining in more details for the first model here. So we wanted to see if we can model the dielectric permittivity with the composite basic mixed law equations. And we wanted to start with the Deleuze model. model. So this model was a good fit for us because it is for the heterogeneous mixtures, and soils are containing water, air, and soil solids for different cases. So this was a good fit, and this equation is also helping you to model randomly distributed components. And basically what you have in this equation, first of all, your target, which is the effective permittivity of the soil system. And on the right-hand side, you have effective permittivities of the individual components of your soil system. Could be your soil solids, air, or water, depending on what type of medium we are talking. In addition to the individual permittivities, you also have a volume fraction corresponding to this each individual component. So far, it is basically you have a little bit of that and you have a little bit of this, and the overall effective permittivity is just a combination of them. But we have a very important factor here, which is called depolarization factor. This factor is actually giving us a good amount of flexibility to model the shape of the materials that we have in our soil. So it is basically a function of the shape and in the 3 dimensions. So it is basically by choosing different depolarization factors, you are modeling the geometry, let's say soil solids in 3D in the 3-dimensional state. And it is also important to know that the polarization factor of each material is unique. So this is actually a good information. However, finding the right depolarization factor could be tricky sometimes depending on your material type, but we are lucky when it comes to that because we have some special cases of depolarization factor known in the literature. So we have 3 different special cases. The first one is sphere-shaped particles, and if you assume your soil structure is mostly consisting of sphere-shaped particles, this is the depolarization factor that you are going to use. For the disc-shaped particles, you have another depolarization factor here, and for the needle shape, you have another depolarization factor. One important and very interesting thing is that for the clay-dominated soils, it's actually known in the literature that disc-shaped particles are representing the depolarization factor for those kind of soils. So we wanted to see the effect of this depolarization factor on the modeling efforts. So we wanted to use Top et al. 1980 equation, even though it seems like it's an old equation, it is still commonly used. That's why we decided to went with that. In addition to that, we already knew that Top et al. Did all the experiments to come up with this equation for the mineral soils, for the clay-dominated soils. So as I suggested by the literature, we were hoping to see that disc-shaped water, for example, in this case, disc-shaped modeling, disc-shaped depolarization factor will help us to capture the behavior that we have seen for the Top et al. Equation. And when we did the modeling, if you take a look at the first graph here on the left, you will see a good amount of match between the Top et al. Equation and the disc-shaped water. So it was good news that, you know, it actually showed us that this depolarization factor can be a tool to, you know, to decide what type of structure you have. And we also wanted to see what would be the results for the sphere-shaped water molecule. So we this time used the same equation with a different depolarization factor and then compare it with the Top et al. And as you can see here, we see a big difference when it comes to dielectric permittivity between Top et al. Equation and the sphere-shaped water. And if we take an even closer look at the second graph, you will see something similar that we observe in our laboratory experiments too. So if you remember, we said that overall trend was more like a bilinear trend where you have 2 distinct parts with different rate for the electric permittivity change. And we were actually able to see and capture that trend with the modeling effort for a sphere shape. And it is actually good news for us because you imagine for the granular medium, you imagine that the structure is more like a sphere shape than the disc shape structure. So this actually right now is giving us some hope to do further analysis to understand this composite modeling of the electrics. And in the second part of my presentation, I will talk about the metric suction sensor. So if you remember, for the metric suction sensor, Teros 21, we don't need any calibration equations. The moment you install the sensor, it will give you the metric suction, which is good news. However, there was just one thing that is stated by the manufacturer, that you need to ensure a good hydraulic contact between the sensor head, which is here with the metal screening, and the surrounding soil that you are planning to get some metric suction data. So let's look at the definition of a good hydraulic contact and poor hydraulic contact. So there are actually two aspects of ensuring proper hydraulic contact. So first one is, so the head of the sensor has a metal screening, and this metal screening has some openings. So the first step is actually ensuring that you are filling the openings of this metal screening. So on the left, we are seeing a good contact where all the openings are filled with a native soil, and in the second picture you see some voids, which is probably going to alter your metric suction results. And the second part of ensuring this good hydraulic contact is actually coming from the installation technique that is again suggested by the manufacturer. So manufacturer tells you that go ahead and take your moisture metric suction sensor and take your native soil and add a little bit of or desired amount of water to bring the native soil to a slurry state. So, and then once you bring this native soil to the slurry state, it is expected from you to pack that slurry conditioned soil around the sensor head. So this seems again doable for the fine grain materials because you have a good amount of cohesiveness that is going to help you to pack this, slurry around the sensor head. However, we weren't too sure how this will work for granular materials. So in addition to having, granular gradation, bigger, coarser gradation, we also knew that our granular mediums are lack of cohesion, but we wanted to see how that one will work. So what we did is we have two options here for the slurry. Let me start with the option one. So in the option one, let's say that we are going to install this sensor into the limestone soil or limestone compacted borehole. So what we did for the first option is, first of all, we use a sieve, and then we basically remove the coarser part, and then we add some water to bring this native soil into the slurry state. And let's see, let me just change the pointer here. Okay, so let's see how that one worked for us. So we add a little bit of moisture to bring this, again, this native soil to the slurry state. And basically we try to pack the slurry around the sensor. And as you can see here, it didn't work very well for us, even in the laboratory. So at that point, we knew that if this is hard to do in the laboratory, it is probably impossible to achieve it in the field. So we decided to have another option for the slurry material. We said that let's add a little bit of clay. Not just, it could be any type of clay, but we were lucky because the entire natural subgrade for the MnDOT facility is clay till. So we had a lot of clay. It wasn't a problem for us to find it. So we said that let's add a little bit, not too much. We don't want to change the entire characteristics of the slurry, but we just want to add a cohesive component into this mixture. So we add a little bit of water to bring this mixture to the slurry state, and let's see how that one worked for us. So as you can see here, it is much more durable compared to just using limestone, the native material, as a slurry. So in terms of the application, it was actually quite successful. But we also wanted to see how these, using two options are going to affect our results. So we prepared identical compacted specimens with the limestone. In the first one, we use the sensor with the option 1, which is just using the limestone, the native soil. In the second one, we install our sensor with the slurry consisting of limestone and the clay. And we basically wrap them and cover them to prevent the moisture content. What we were trying to achieve here is to see if there is going to be any big difference in terms of the metric section equilibrium, or even for the hydraulic equilibrium time. So after letting this 2 specimen come into metric section equilibrium, we realized that the results are actually yielding very similar metric suction. So this was a good news for us in terms of having more confidence to use this new developed technique, which is the option 2. We wanted to see also the performance of this suggested limestone plus clay slurry technique by doing drying method soil water characteristic curve. So at this point, we were lucky because the material that we were working, which is the limestone, already had a soil water characteristic curve determined by the traditional method, which was the pressure plate. And what we did is we prepared another identical set of testing with the same compaction degrees and with the same moisture content. In one of these molds, you have the sensor with the native slurry only. And in the second one, you have the suggested modification to the slurry, which is limestone plus clay. So what we did is after compacting it, we just let them dry. We kept taking weights of this molds while taking corresponding metric section, and we were measuring the moisture that is being lost during this drying, and we see as a result we have seen that both of the slurry options, option 1 and option 2, yielded actually very similar results with each other, which was good news, which told us, okay, now we are even more confident to use this in the field. And we also see something additional, which was actually the results that we were getting with this Teros 21 sensor. They were very comparable with the ones that is obtained with the traditional method. This was also good in terms of capturing the true soil water characteristic curve behavior. So we use the slurry technique, which is the second option, adding a little bit of clay for the remaining recycled materials as well. And if you take a look at here, you are seeing 4 different sensors with 4 different colors of slurry material. Each of them had clay, and that's actually the reason you can pack this slurry material around the sensor head. And they were all successful to give us a soil water characteristic curve for the recycled materials as well. And after doing this extensive research in the laboratory, we went to field and we started installing our sensors. So instead of using a screwdriver in the field, we use a tool, pilot tool, we can name it, to install the volumetric water content sensors. And as you can see here, these pictures are showing actually a perfect installation. However, if that is not your lucky day, there are chances that you're going to try to install this sensor into a very granular spot for that elevation. And it happened to us. And what we did is basically you are trying to stay in the same elevation, but you're trying to find another spot that you can install this sensor. So if you're still dealing with the granular materials, there's always chance that you're not going to be able to install the sensors right where you want. But of course, our technique is helping us for sure, and it made the job easier for the 90% of the time. For the metric section, as you remember, the entire natural subgrade of the MnDOT facility is clay. So what we had is the native soil, and we add a little bit of clay. And as you can see here in this video, it worked really well for us. So we have our cut here with the sensor installed. So overall, we did, I believe, very successful installation as a teamwork. So overall, we installed 108 moisture sensors. 54 of them were Teros 10, and the rest of it, half of it was Teros 21. And let's I wanna finalize my presentation but with the field efforts and updates. So before showing some results from the field, let's talk about the initial survival rates here. So it seems like for both of the sensors, we achieved over 90% initial survival rates for both of the sensors. And here right now, in addition to the initial survival rates, right now we are looking at two graphs. On the left-hand side, we have volumetric water content, and the right-hand side, we have matrix section graph for the same cell. And let's take a look at now our cell cross-section to understand what are these actually corresponding. So we have base layer, subbase, and subgrade. Of course, there was an HMA layer on top of the base, but we're just focusing on the foundation layer here. So we have our moisture sensors installed each layer, and we have one set of sensors. So when I say moisture sensor, I actually mean both Teros 10 and Teros 21. They are in the same elevation, very close to each other. However, they are not interfering with their volume of influence. So we were good for that. We have one set of moisture sensor in the base. We have two sets of moisture sensors for the sub base, and we have one in the subgrade. So now let's take a look at the volumetric water content. So as you can see here, we have subgrade at the bottom with the high volumetric water content. We have subbase bottom, subbase top, and base. If we focus on the day 100, we observe for each of these layers, we observe a drop in the volumetric water content. And if we look at the same time for the matrix section graph, we actually see an increase in the matrix section corresponding almost the same time period, which showed us that these sensors are working consistently with each other, which was a good news for us. So as a summary, with the study, we were able to say that composite modeling of the electric permittivity might be an efficient tool to determine the relationship between the dielectric permittivity and the volumetric water content. We have also seen that this relationship is bilinear, apparent to be bilinear, and it's also a bulk property, and it's not changing depending on the compaction degree. We developed modified installation technique, which we think made the things easier in the field. And we also seen that Teros 21 matrix suction sensor actually yielded very comparable results with respect to soil water characteristic curve testing done with the traditional equipment. And overall, as a result of this efforts both in the field, in the laboratory, we were able to achieve over 90% of initial survival rates for both of these sensors. So we were able to achieve this high initial rates. We say high because we have been told that the initial survival rates for the previous cycles of construction was around 70 to 80%. So we see an improvement for that. And we believe that there are two main reasons for that improvement. The first one is the extensive fundamental research we did in the laboratory. And second of all, highly experienced MnDOT staff who already had a lot of actually experience on the moisture sensors. However, so far we weren't able to see the long-term survival rates because we just installed them last summer and the reliability when it comes to having a long-term performance. And we actually haven't investigated the effects of the environmental conditions, which is the sensor exposing to the freeze and thaw cycles and also the traffic loading. So overall, what I'm trying to say here, there are still some unknown that might affect the long-term survival rates when it comes to this sensor. However, we are confident to say so far we are achieved over 90%. So by saying that, that will be all from my side. Thank you so much for joining us today, and we would be happy to answer your questions.
Wonderful. Thank you so much.
Yeah.
I have not seen any messages. Oh, I missed one in the chat.
Okay.
So from Timothy, can you translate the Teros 10 measurements into gravimetric water content? I'm guessing it's just a math exercise with specific gravities. And
Yeah,
maybe you've-
so it is basically the bulk density multiplied by the gravimetric water content, which is equal to volumetric water content. So generally, you can assume that whatever you are seeing as a volumetric content, divide that by 2, and it will be very close to the gravimetric water content that you have, but also it depends on the bulk density.
Thank you, Tim. I'm very happy to see you online, Tim. We miss you here in the research section, and that you have the geotech mind. So yes, I know what you're going through. Like, we are not used to seeing and thinking in volumetric terms.
Right.
Yes,
Right.
so very good term, and I think yeah.
Thanks. I'm still a research geek at heart, even though I'm a little bit removed from it now, but thanks. Good work.
Thank you.
Thank you for the question. Thank you.
There is a hand
I
raised.
see a hand.
Yeah.
Yes, please, Sadar.
Hi, interesting presentation. My name is Sattar Dorafshan from UND, University of North Dakota. On your slide 11, so you have 2 values. I'm wondering which one is measured as a ground truth or basically the actual water content. So you have one that's measured by the sensor, correct? And what's the ground truth? What's the actual water content? How did you measure that?
So what we did is, thank you for the question. What we did is during for the different volumetric water content, so we were compacting new specimen from the beginning, and we knew its bulk density since we are doing the compaction by ourselves, and we took gravimetric water content samples and we oven dried them. And then since we have the bulk density and since the other day we have this gravimetric water content, we just obtained the volumetric water content for the experimental data.
Thank you. And then the follow-up for me would that be, is there like when you're in the field basically, this still requires contact, right? So you have to prepare and dig a hole and get that instrument installed one way or another. I guess so it's work based on dielectric, and I might be wrong here. I'm not a geotechnical person, but I think maybe GPR also measures dielectric properties of a surface without contact. Are there any benefits between the two? And again, I might be wrong. Maybe GPR does not do what you're doing at all. That's ground penetrating radar.
You're right, actually, and we're working closely with a colleague here across my office here, Dr. Segeye, who is doing a lot of that GPR work, and there has been at least 2 publications on that topic. So you're absolutely right. We're trying to improve that technique, use easier than non-contact one. That there are other cons about using it, but there is a strong correlation, and I will be more than happy to share some of those data. But you're absolutely right. GPR is based on the electric as well, and we are hoping that we validate that some of the results are coming from this research, and the instrumentation placed in MnDOT will help validate the measurements that the road doctor and Dr. Segeye's program are doing to make things faster, as you mentioned, the non-contact. Yeah, so you're right about it. Yeah, thank you for the comment.
Thank you. Yeah, that's interesting. I'd be interested to look into it and see because I have something, not GPR. I have a hyperspectral camera that are supposedly great for moisture content detection, but it's only surface. So it would be interesting to see what you have on GPR. My last question, I promise, is do you guys have any recommendations in terms of field moisture measurements when your granular material gets bigger? Let's say you have crushed aggregates only, right? Not soil. And do you think any of those sensors work, or based on your experience with them, any of them is going to be better than the other?
Oof, that's a tough question. So I think for granular, for bigger particles, it will probably not work. Yeah. We'll probably have to go the another route. Yeah.
Okay. Especially for the volumetric water content.
Yeah.
Because you basically need to have a good contact between the needles and also surrounding soil. So you can I think you can overcome to granular medium with the slurry option that we created here. However, yeah, it is going to be a tough thing to make sure that that's exactly what you have in the field that you're collecting. Yeah.
Very good. Thank you so much.
Thank you. Thank you for the questions.
Okay, there is another one.
Yes. Okay.
Yes, we have a couple more questions in the chat. One is from Andrew. What is the difference between the TEROS 10 and 21 sensors? Is one the volumetric sensor and the other the matrix suction sensor?
Right.
Exactly. Yes. One is measuring the volumetric water content, which is TEROS 10, and the other one is measuring the metric suction.
So the idea between having those two very close to each other is to develop the in situ soil water characteristic curve. So we have the whole picture of the unsaturated flow. So that's what we're trying to push to the next level in terms of advancement of understanding how the foundation is working. Is getting that whole full unsaturated flow picture by having those two sensors very close to each other, is to have the in situ soil water characteristic curve that will allow us to predict in a better way the flow of water in the pavement foundation, because most of the time is in an unsaturated regime. That's a good question, Andy. And then the next one.
Yes, is from Mateus. What to do if the shape of the particles is angular or not of a defined shape?
Yeah, really good question.
This is what we're working on, trying to define, playing with the polarization shape, because of course sphere is not the ideal situation for the water shapes in our granular media. So we're trying to statistically play with it. What is the right parameter? And Ceren didn't show, but in these papers that we referenced, actually, those polarization functions are actually a function, not just a number, but it's a function.
Aspect ratio.
Yeah, so it depends on the aspect ratio of the particle. So what we're looking at next is to get images of particles, shapes of the particles, and come up with those kind of a hybrid shape and determine what is the right polarization. So that what we were showing is just a preliminary sensitivity of the models to see if the models were able to capture the overall behavior. And we were very happy and surprised that kink, the bilinear situation was actually being reflected by changing the polarization factor. But that's a good question. That's something that we're gonna further refine in the modeling efforts. That's a good question.
All right, and then Ahmad asked, have you ever tried these sensors in concrete?
So TEROS 10, no, but TEROS 12, which is actually a little bit more sophisticated than TEROS 10, but it's just the same principles. It just includes temperature measurement, has been used by the NRRA concrete team. Tom Burnham and his team use it to monitor curing. So it uses the electric. And I'm very curious. We'll like to then look at the trends, because it's a very complex process, the curing. But yes, to say basically to simplify the answer is yes, they have been used. TEROS 10 no, but TEROS 12. Now we haven't dig into data and modeling of it, but I hope we can start doing some cross collaboration.
And great. And then Mateus just followed up with maybe some modeling and parameter estimation could help. And that had to do with the shape of the particles. Yeah.
Absolutely.
Exactly.
Thank you, Mateus.
All right. Well, last call for any questions or comments. Oh, and I do see a hand raised.
Yeah, Satar.
Again from Satar. Yep.
Hi, sorry, I promised the last one would be my last question. I just thought
No
of another
worries.
one. So in your basic assumption, you are assuming that there are certain amounts of dielectric properties of air. That's the porosity in the soil, right? I'm wondering if you have tested the soil in an oversaturated state, and if these sensors can actually, or the calibration equations can actually be used for that, because then now you use that dielectric one, right? Because all the pores are filled. Have you done that? Does it work with supersaturated status?
So we try to do that. However, the problem is the compaction degree that you're going to achieve, or even the compaction with the saturation. So actually the last data points are very close to saturation. If I go there, last data points should be very close to saturation, but we weren't able to proceed further because, with this granular materials, it is actually impossible to keep the structure as saturated once there's, excess amount of water. But we can basically say that these last points for each of them are actually very close to the saturated state.
Thank you.
Yeah, sure. Thank you for the question.
All right. Well, I'm not seeing any other raised hands or comments or anything in the chat, so I think we will close this out. But thank you, Raul and Ceren. And yes, I'm seeing some applause hands on the bottom of the screen. So thank you to all of you for joining us today once again, and we will hopefully see you next time. And everybody stay safe.
Thank you, Laura.
Thank you so much. Everyone. Thank you.
Thanks.
Stay safe.
Thank you.
Thanks, Ceren. Thanks, Raul.
Thank you.